Hello physics class. Today's lesson is the last material of the unit, circular motion. Tomorrow there won't be any new topics. There'll be about an 8 or 10 question unit assignment that won't take you too long, and we'll wrap things up. Start the next unit next week, okay, which will be work and energy. There'll be more math in that unit than there has been in this one. All right, I hope you found it interesting. Today we're talking about satellites. And I kind of got you introduced with it in a assignment question yesterday that involved the International Space Station. Okay, what I want you to just have in your mind right now is that artificial satellites, all that means is not the moon. Okay, artificial satellites orbit pretty close to Earth. The International Space Station is really close, actually. It's 408 kilometers up. Okay, compared that to the size of Earth, this is totally unscientific, but it might look something like this. Okay, so the ISS is less than 1/10 the radius of the Earth up. So it would look something like this if you drew it. The ISS is not that big, but just to give you an idea of its location, that's Earth. There's the ISS. It's really, really close. I'm going to add to this. I'm going to show you where other satellites might be located, as well as where the moon might be. Because you might be thinking, would be the moon here, the moon here, the moon here, the moon not even in this room. We'll find out. Okay, we're going to do those calculations. So I want to tell you about geostationary satellites. These are super common. Geostationary satellites orbit above the equator, and they have a period of 24 hours. So as the Earth rotates, the satellites move locked in position because they orbit the Earth in the same amount of time it takes the Earth to turn. Okay, so they remain locked above the same point on Earth at all times. A lot of satellites are geostationary because they're easy to locate. They're easy to communicate with. They're always in the same spot. That makes a lot of communication satellites geostationary. I don't know what it's like anymore. I haven't had satellite radio in a long time, but I recall having satellite radio and driving up north in the Yukon, and the farther north you get, the worse the reception would be, and it would cut out if you went into a river valley or something. And that's because it's communicating with a satellite above the equator. And as you get farther north, you get farther from that satellite. And if it loses its line of sight, like if you go into a valley a little bit, you will lose communication with that satellite. So I always found that interesting. That's something unique to living in the north, losing communication with geostationary satellites. NWT is probably a bit nicer because it's much flatter than the Yukon, but I'm sure it still happens. All right, so what we're going to do is find out where these are. We're going to find the altitude of geostationary satellites. Okay, there's a couple ways you can do it. You could use Kepler's third law and data with the moon. What I'm going to do is equate these two formulas, just the general moving in a circle formula and our orbital speed formula. Okay, so check me out. I'm going to say 2 pi r over t equals orbital speed of gm over r. Okay, this is going to be pretty mathy, but it's going to work. So what we're trying to find is r. We know what t is. T is going to be that 24 hours. We'll have to put that into seconds, but I'll do that. Let's do it right now. So take 24 hours times 60 times 60. It's going to be 86,400 seconds. So we know what t is. M, remember in that formula, m is the mass of what's being orbited. That is going to be of the Earth. Okay, I tried to fool you on that yesterday. I hope I didn't get you. So there we go. And now again, it's not the easiest equation you'll ever solve, but we're looking for r. Okay, I hope you had this instinct. If we square both sides, it's going to look a lot nicer. Okay, so the right's going to be 4 pi squared r squared over t squared. The left is just going to be gm over r. Square root's gone. Now I got to shuffle this around. I'm going to cross multiply a little bit. Get the r's together. And the t is going to go onto the right.